Okay, let's start. So we are back. I'm gonna be solving the weekly contest 358. Just shared the link. Let's start with Q1, which is I'm sharing the link. It's an easy, and it's called max pair sum in an array. So you're given an integer array called nums, and you have to find the maximum sum of a pair of numbers from nums such that the maximum digit in both numbers are equal, or -1 if there's no such pair. And we have two examples. So here the sum is 88, and the maximum, yes, for example, if we choose 71 plus 17, which both have maximum digit 7, and their sum is 88, and that seems to be the maximum. And then in this case, since they are all one-digit numbers, there's no coincidence, no duplicates, so there are no pairs that satisfy the condition, so we have to return -1. And so here we should pay attention to the constraints. As expected for an EC, the size of the array is very small. It's only 100 at the maximum. Okay, so this is a classic pair search problem, which are very common in LeetCode. So the order of the number of pairs is n squared, and n in this case, as we just said, is at most 100. So 100 squared is 10,000. So we can get away with a brute force search. We can enumerate all the pairs, check for the condition, and then maximize the sum. And that should be good enough. Remember always, when you are deciding what algorithm to use, you don't have to choose the most efficient algorithm. You have to choose the simplest algorithm, the quickest to implement, that is good enough for the constraints of the problem. And you can make a rough estimate on the number of operations, iterations of the loops that your program is going to execute in the worst case. And usually if it's roughly below 10 to the 7, it's good enough for LeetCode. So there are some exceptions, but that's a good rule of thumb. So without further ado, let's code it. So this is very standard code. Let's set the size in a variable for convenience, and let's go over all the pairs of elements without repeating. So this is two nested loops, and we start the inner loop from the next element of the variable of the first loop, the outer loop, and there is a condition, which is that the maximum digit of each number has to be the same for the pair to count. And there's a very easy way in Python. We can convert it to a string, and then we just get the max. And why does that work? That works because the order of the, I mean, when we convert to strings, we are dealing with strings of one character, and the order of the characters is the same as the numeric order, and that's why we can use the max function, and this should work. And here, if they satisfy the condition, we want to consider the sum. So here I repeated I, it should be Shay, and we consider the sum, and we need to return the maximum. However, we already know that there's a case where there's none, so we have to use a default value, which it's -1. So this kind of a one-liner, yeah, maybe we can actually make it a proper one-liner. Why not? Just for fun. And this should work. So we get the examples right. I don't think there's any other edge case. We already have an example. This is very generous from the problem setters. We get the edge case in the examples. So let's just submit. Why not? And accepted. Pretty good. So that was not a big deal. But let's think about it a little bit. I'm going to try to solve the problems in different ways, because I think that's a good way to learn the concepts and not just one specific way to solve them. So let's try to find a faster way to solve it. Maybe a linear way. And let's get rid of this. So we know that the only pairs that count are the ones that have the same maximum digit. So that means that we can partition the elements of the array by their max digit, by this key. And we only need to consider pairs within the same class, the same part in this partition. So we can start by doing that. How do we do that in Python? We can use default dict. I like to decompose the problem and write functions. So we'll call it group by because it's pretty much the concept here. And we are going to have default, let's call this groups to be more descriptive. And we are going to go over all the elements, and we are going to use as the key the max digit in the same way that we computed in the previous solution, and we append the value to the group. And that is pretty much it. But then we don't care anymore about the key. We just care about the groups of numbers. So let's just return the values of the dictionary, and that's going to give us what we want. And then, hey Dix, what's up? I'm solving the weekly contest from a couple of weeks ago. So let's keep going. So now we want to go over the groups. And so it's easy to see that for each group, we don't have to try all the pairs. We know that since we want the maximum sum, if the group has only one element, then there's obviously no pair. So we can check that. If the length of the group we want it to be greater than 1. Okay, and if that's the case, we want the let's imagine that we have a function, why not, that gives us the top 2, why not, and we want the sum or the max 2, however we want to call it, and then we want the maximum of all the groups, just like before. And again, there's a case where there's none, and we want to return -1. Okay, so how do we implement this max2 function that we invented? So a very simple way, which is not the most efficient, is to just sort them and return the last 2 elements. Is that correct? Yes, I think it is. And that should work. Hey, smart coder. You'll be driving? Okay, don't. Be careful. Okay, so this is, oh no, I run the examples are good and accepted. So the solution is much faster, since here we are accessing a hash map, which is how the dictionary is implemented in Python, if I'm not mistaken. So this should be linear time, and this is n log n because we are sorting. So this is much better than the previous solution in terms of runtime. Of course, we didn't need this for the contest. Let's make that clear. But here, we don't actually need to sort, right? Because we only need the 2 maximum elements. We could do this by keeping 2 variables with the maximums, the top 2 elements so far, but there is already a function in Python, which is from the heapq library, which gives you the n largest. In this case, we need 2, and this should work. And in that case, we remove the logarithmic factor from the order of complexity, which is not a big deal, to be honest, but it's a nice, in some other cases it could be important, I guess. So yes, I think that's pretty much it. Let's review at a high level what we did. So again, this is a kind of a pair search problem. We have to find pairs that satisfy some condition, and we want to aggregate them with a maximum function. This is very, very common in LeetCode. We first went for the brute force search solution. We enumerated all the pairs. We first, this is very important. We first make sure that that solution, the brute force solution, was good enough. Whenever a brute force solution is good enough, go for it. Don't try to make it more efficient if it's not necessary. And then just as a follow-up, we try to make it linear instead of quadratic. And we also, I think one important lesson is how we decomposed the problem into little problems and sweet functions that do only something a little general that doesn't have that is independent from the rest of the problem. That's usually a good thing when you can break it down this way, your code. Anyways, so yeah, this is the Q1. Let's go to Q2. Let me share the link. Double a number represented as a linked list. You're given the head of a non-empty linked list representing a non-negative integer without leading zeros. Return the head of the linked list after doubling it. So yes, I mean, I already did these problems in advance to prepare a little bit this class. I'm clarifying this so that you don't have the impression that I'm just figuring this out as I read them. But yeah, I wanted to say that this problem is a little unfair because they're asking you to, they're asking you to double a big integer. And I say it is unfair because in some languages like Python, you already have support for big integers. So I think in that case you have an advantage with respect to, for example, C++, where you don't have that support in the standard library. And also linked lists problems are, I don't think they're good problems for contests because you can always convert from a linked list into a regular list, do all the work, and then convert it back to a linked list, which usually is not the spirit of the linked lists problems, but it is what it is. This is a medium problem. So, and the length of the list is up to 10 to the 4. So this is a very big number. It's 10 to the 4 digits. And this is important because it doesn't have leading zeros, but there is an edge case, which is when it represents the number 0, it has a 0. It's not the empty list. It's a node with the value 0. And we should pay attention to that because it could be a potential bug. So I'm going to do a solution that takes advantage of the big integer support in Python. It's not a big deal to implement the doubling of the big integer, but I don't like this problem that much, so I don't want to go over more than one solutions if I don't have to. So this problem is in some way it's about representation. We want to change the representation of the number as a linked list of digits into an int in Python. Then we double it and then we convert it back into the linked list representation. Okay, so this is a very common processing task in programming in general. And there's a very easy way to break it down. We can have one function to convert a list to an int, and then another function to convert an int to a list, which is the inverse of the function. And that's a very clear way to break down, to decompose this problem. So let's say that we have a list to int, and this is usually called head here, and let's imagine that we already have this implemented. Here there's an int. So this is going to be clearly the interface of these functions. And if we imagine that we already have those, we can solve the problem very easily by using list to int of the node, then we just multiply by 2, and then we convert it back into a list. Okay, so that's easy enough. And now let's implement them separately. So we want to traverse the list, which is a very standard code. We want, while the head is not none, means that we have more elements, and we want to advance the header, the head pointer, and we're going to keep track of the number here. It's important to notice that the order of the digits in the list is from most significant to least significant. So that means that we have to, when we add a new digit, we want to multiply, we want to shift everything we already have to the left, which is in base 10 is to multiply by 10, and then we want to add the current digit. And this is it. This is going to do what it says. It's going to convert the linked list into an int. And now we want to do the inverse. And here we need to, again, we need to take into account that we want the list to be from the most significant digit to the least significant. But when we process the number, it's easier to process it from least significant because we can use the modulus operator. So this code right here is going to give us the digits from least significant to most significant. So that means that we need to create the list from the end to the front. So it's not a big deal. But here we want the result pointer to have a new node. We want to add this digit, and we want to make the next pointer pointing to the current head. And this should work. But there is a catch here. Like I said, we needed to take into account the edge case where n is 0, because since the condition of the loop is that n has to be greater than 0. If it's 0, we are going to return none, an empty list, and that's not what we are expected to return. And this is unavoidable because the zeros to the leading zeros only matter in that special case. If we do something that ends up adding one leading zero, it's not gonna work for numbers different than 0. So I think the easiest way is to just have a special case here. If any 0, we return a list node, which by default it's exactly what we want. It's value 0 and no and an isolated node. So this should be good enough. And it works for the examples. Let's make sure that it works for the edge case that we handled. I mean, it should work because we added an if statement, a special case, and it makes sense. So let's submit. And accepted. Cool. So yes, I think the takeaways from this problem, the main takeaway is, well, I'm not going to repeat what I said about the big integers and the advantage that Python has. I mean, the doubling, we did the doubling very easily. Like just, I mean, it's trivial. If you are doing this without support, you'll have to, I mean, the common way to do it is to go from the least significant digit and have a carry variable and multiply the digit by 2 and carry and so on. It's not hard to do, but if we don't have to do it, it's certainly easier to do this. But I think the main takeaway here is how we decompose the problem into how we abstracted the problem into a representation problem. And that led to breaking it down into these functions which have a very simple interface, and even their implementation were very simple as well and very standard once you already know how to deal with linked lists. So yeah, I think that's all for this problem. Let's go to Q3. The other one was a medium, right? Let's go to problem number 3. This is a medium as well. Minimum absolute difference between elements with constraint. With constraint, okay. So we're given an integer array and an integer x. We want to find the minimum absolute difference. Absolute difference you can think about in terms of distance in the number line. Between two elements in the array that are at least x indices apart. Well, two elements in the array, so this is yet another pairs problem like Q1. But probably, since this is a medium, probably this is a bigger size. This is a very common size, maximum size. And essentially what it means is that you cannot do an n-square solution, because that would take roughly 10 to the 10 iterations, and that's too much in LeetCode. That might take like a minute in a standard computer, I guess. Or at least more than the time limit. So here, in other words, well, here they define it in a more formal way. But I mean, usually you can skip this unless it's not clear from the first part. Okay, and we need to return the minimum distance. The numbers can be big, the values of the numbers. Okay, so here we need a quick way to deal with pairs. And there are two parts to this problem. First is that the distance within the array has to be at least x. And one way to deal with that is to go over the array from left to right, for example, and leaving a space of size x and adding the elements of the that are at distance x to some data structure, and then we can query that data structure to find the closest element to the current element. This is going to be clearer when I start writing the code. So with that approach, the problem reduces to finding a data structure that can solve this kind of query of finding the closest value to a given value quickly. Of course, not in linear time. And it has to be a data structure. We're going to do queries. We're going to be adding elements and querying for this mean distance operation. So it cannot be a static. You cannot sort like an array and then do some binary search, because then you cannot update it quickly. In other words, we need two operations to be quick: the add operation and the mean distance operation. And in the case of Python, this mean distance operation can be well, not in the case of Python. I mean, we can think about this mean distance operation in terms of a very common operation, which is the rank operation. We have a value and we want to know the ranking in a set of elements or a multi-set of elements, which is essentially the insertion point in the set, in the sorted set. These kinds of operations are called order statistics. And now, in the case of Python, there is a data structure that does this, that is not part of the standard library. However, it is available in LeetCode, and it's called the sorted list, and that's what we are going to use. And sometimes this structure seems like cheating. I mean, of course it's not cheating because it is available, but it makes solving some kind of problems very easy. So we're gonna keep track of the elements that are far enough from the current, okay? Because we also have that condition, as we said, and in this case we want to minimize, so we are going to keep track of the minimum so far, and when you want to minimize, the default value or the initial value can be infinite. In this case, So there's always yes, there's always going to be an answer, right? Yes, because x, yes, for example, is the number of elements is 1, then s has to be 0, and in that case, yes, I mean, they could be, the pair could be the same element when x is 0. So that means that there's always going to be an answer, so we don't have to worry about returning infinity. So then we call this R because it's going to be the right element of the pair that we are considering, and we want this to start from x, so that, because if this is a right element and the index is less than x, then there's not going to be any element which is far enough. So we add the, hey Amuga, thanks for the follow, thank you very much. So we add this element here. So that means that we're going to keep the invariant that all the numbers that are far enough are inside the set. And so eventually we're going to return res, and we want to minimize. So this is the standard code for minimizing. And here let's write, I like to decompose the problem. So let's write a function that is going to give us the minimum distance of this value to any of the values in the set. And let's see how we can implement that. And so this data structure, this sorted list, has a bisect left method, which gives you the insertion point of the value x in the sorted list. If the insertion point to keep the list sorted. Okay, this is the same idea as the bisect left function from the bisect module of the standard library. And now we want to so this is the insertion point, right? So that means that the ith element of the list is greater than or equal to x. Okay, so that is one candidate to be the closest to x, but the previous element, so the I-1, is also a candidate because the closest one could be less than x. So that means that we want to check two values, the I-1 and the I. But I don't want to repeat, I don't want to duplicate code, so we can do a slice operation in the sorted list, and this is going to work. This is going to give us these two elements that are the candidates. None of the others could be the closest because they are or either greater than the ith or less than the I-1. However, there is a catch here. Well, first of all, this is exclusive, so it's not I. What we want is I+1. But there is a catch because I could be 0. If the element is less than or equal to all the elements in the set, I would be 0. And in that case, this is going to be -1, which in Python it's the last element. So that will result in a bug. So one way to deal with that is to do this, so that if we get -1, we're going to get 0. And in this case, we also could be, it could be that I is the size of the set. It could be that there is no element I if X is greater than all of them, for example. But in this case, it doesn't matter because there is no wrapping around for the indices that are greater in Python. So this should give us the range of elements that we want to check. And then it becomes a simple minimization. We want to minimize the distance. So let's call these elements I, because we call this X, and we want to minimize the distance between them. And that's pretty much it, I think. And we did it without duplicating code, which is usually a good thing. I mean, if you're in a hurry in a competition, you don't need to. You can copy paste, of course, but if you can get away with not duplicating, then it's easier to understand your code. Okay, accepted. So that's good. So the takeaways are, so make sure that you have some data structure that supports these kinds of operations like bisect left, and that you can add elements quickly. In C++, there is also a non-standard data structure, which is this kind of structure is called order statistic tree. Or at least a kind of implementation of these operations is an order statistic tree. And I know that for C++ there is one, I think it's GCC extension. It's been a while since I coded in C++, so I don't know, but I'm sure that that extension is available for, because one of the guys in the community told me, and I checked it. So this kind of data structure is very important for interviews or for LeetCode problems. So make sure that you don't have to understand how it's implemented internally initially. If you understand the interface and the guarantees in terms of order of complexity, then you can use it. And that's true for everything, right? For data structures and for algorithms. You can sometimes, maybe initially, you can sometimes use them as a black box and only know their interfaces and their order of the order of complexity of their operations, the main operations, and you can solve a lot of problems like that. Maybe there are problems that require some tweaking of the internals, and for that you need to know. But for these data structures, you usually don't need it. For example, in the case of sorted list, I was hesitant to say that these are always order statistics trees, because my understanding is that the sorted list of the sorted containers are actually use a different kind of implementation, which I think don't have the optimal order of complexity. However, in practice, due to the way that they are implemented, they are very cache efficient. and they work in practice. They work very fast, and I never got a TLE using sorted list. And I think they use a technique called square root decomposition. You can look it up. It's kind of advanced, but it's very interesting. So yes, I notice that here the two conditions are kind of independent, right? Because the X condition is you could remove it and the problem would be similar. If you didn't have that condition, you could use the same solution, but instead of starting here, well, I guess it's the same when X is 0. In that case, there's no restriction. So yes, it's a special case of this problem. But my point is that it doesn't change much to add this extra condition. I mean, you need to know this trick, but I think it's easy to figure out even in a contest. So that's it for Q3, and let's go to the hard one, Q4. Let me share the link. Apply operations to maximize score. You're given nums and positive integers and an integer k. You have to maximize your score by applying the following operation at most k times. Choose a non-empty array that you haven't chosen previously, subarray, sorry, and you choose an element from the subarray with the highest prime score, which they define here. So let's see what it says. If there are multiple, there's a rule to break ties, the smallest index, and then you multiply the score by x. And here they define what a subarray is, which we already know because it's very common here in LeetCode. And the prime score is equal to the number of distinct prime factors of x. We get an example, okay, makes sense. And we want to return the maximum possible score after applying at most k operations. Okay. And we need to do this modulo something, modulo this number, which is very standard. And the size is 10 to the 5. And yes, this is obviously bounded by, this is a number of subarrays, including the subarrays with only one element. So of course k cannot be greater than that, but they reminds us, which is nice. So here I think you get 81. So yes, it's a little hard to follow the whole examples. So okay, my take on this problem, this is not in my opinion, this is not a hard problem. It's more of an overloaded problem, which means that it consists of several things which are required to solve mediums mostly, but they add up, and I guess that's why it's because, for example, the prime score is pretty independent from the rest of the problem. You can pre-calculate the scores for the given numbers, and then you can pretty much no, not pretty much, you can completely forget about the prime condition. You just have a score for each number, and it doesn't matter where it came from. I mean, well, there is a condition that it turns out it doesn't matter, but you can. One observation here is that the number of distinct primes, it's pretty small for the numbers in this range. The values of the numbers can be up to 10 to the 5, right? And that means that the number of unique primes that you can have is pretty small. For example, let's see, if we have the smallest primes and they are all different, that would be 2 times 3 times 5 times 7 times 11. We're already at time 13. We're already at 30,000. And here we already surpassed 10 to the 5, right? Because that's 100,000. So that means that this is already too big. That means that there are at most 6 unique primes. So the scores of the numbers are going to be, I think you can have 0 because 1 is a possible value, and in that case you don't have any prime. So the range of the scores is going to be between 0 and 6 inclusive. It turns out that you can use that information to hack a solution, but if you know the technique, if you know a very common technique, you don't need to know this. But I think it's an interesting observation. Anyways, so I think the crux of this problem is to realize how to maximize the possible score. And the idea that I used was to try to go from the score is going to be a multiplication of the values in the array. So let's try to be greedy, and let's try to start with the biggest x, and let's try to even have it in the multiplications as many times as we can, because that's going to give us the biggest score. And in which case x is going to be the highest prime score? Well, if you consider all the prime scores and you have an element with the highest value, and you move to the right, if you find an element that has a bigger prime score, well, then that is going to dominate. That is going to be the element that you're going to multiply. So you don't want that. You want to go to the right as much as you can without exceeding the prime score of x, the x that you are considering. And similarly to the left, you want to go as far to the left as you can until you find one that is greater. And you have to be careful with this tie-breaking condition, but the structure of the solution is that we're going to go from largest to lowest, and we're going to figure out how many times we can use that value in the product, and we are going to multiply those many times and so on until we run out of operations, which depends on this k value. So that is the big observation in this problem. The rest is just dealing with, for example, for the factorization, and we need to know how we can figure out what is the next greater element for each element in the array. And luckily, that's a classic problem, which is usually called exactly that, next greater element. You can look it up. You'll find a lot of material. I'm gonna explain it a little bit, but you can always look it up and study the solution. And it uses a concept that is useful for other problems as well, which is a monotonic stack. But anyways, let's start coding. So, like I said, we want to try to decompose all the scoring, the prime scores. We want to isolate that from the actual solution to the problem. So let's write find scores that is going to give us, with a very simple interface, it's going to give us a parallel array which with the prime score of each number. And here we can go both ways. We can assume that that's already implemented and go for the main algorithm. I'm gonna start by implementing the prime part. Let's make sure that we don't forget about the modding, because it's very easy to forget about that. And well, the way we can do this quickly, the factorization of every number is with a factorization sieve. I'm not gonna dive deep into how to implement it, but yes, let's find scores. So this is going to pre-calculate a sieve, a factorization sieve, and we want to make sure that we have a sieve for up to the maximum number. And then we want another function. Let's break it down. There's no cost to make many functions as long as they are clear, they are short and sweet. And here we're gonna have a function that, given the sieve and a number, is going to give us how many unique factors, which is a prime score. Well, maybe we can even call it like that, prime score. So here we want the prime score of, using the sieve, of every number in nums. And let's assume that we already have this. So the sieve is going to have, for every number in the range, is going to have one prime factor of that number. So that means that we're going to divide as much as we can by that prime, and that's a unique prime because we're going to divide, like I said, as much as we can, and that means that we need to add 1 to the result. And that is it. And now for the sieve, this is very standard code. You can look it up as well. This has to be the maximum. Yeah, this receives the maximum value that we care about. And so we start. This is a sieve, the same idea as a sieve. We only need to go up to the square root of the maximum value, and if the prime of p is p, then it means that it is prime. And in that case, we want to go over all the multiples of p starting from the square, because all the others were already handled by smaller primes. And we skip, the step is p because we want only multiples of p, and we set p as the prime, as a prime of m. It doesn't matter which one it is. Sometimes I guess it makes sense to use the smallest or something like that, but in this case it doesn't matter. So that deals with the prime, all the prime stuff from this problem. This is pretty quick. The order of complexity of the sieve algorithm is not very easy to calculate. You can look it up. I think one way to approximate it, or at least to find an upper bound, is to think that that this is a harmonic sum, because since we're going over all the multiples, it means that we are dividing the max by p. That's how many times this gets executed. And I think the harmonic sum, which is 1 over 2 plus 1 over 3 and so on, is bounded by a logarithm, grows logarithmically. But look it up. I mean, in practice, it's fast enough for LeetCode. So okay, we have dealt with that. Let's move on to the main problem. So now we want to solve the next greater element problem. Again, this is a classic. Let's call this NGE, next greater element. We only need an array. And we are going to return the next greater element for every element in the array, where the next greater element is going to be the index of the next greater element. And if there is none, we're going to return n, which is a position right after the last index in the array. And this is going to be handy for edge cases. And so we go from right to left, and we're gonna, like I said, we're gonna keep a stack, and the stack is going to be strictly increasing. That's why this is called a monotonic stack. And the reason for that is that if at any point you have an element that is less than the previous element, then that's not going to be the next greater element. That cannot be, because the previous one is greater and it is closer to the element that you want the next greater. That's why you never want to keep elements that decrease in the stack. So at this point we want to find the next greater element of the ith element, and while the stack is not empty, we want to remember that in the stack we put indices, and if the element is less than or equal the top of the stack, in the top of the stack, since this is strictly increasing from the top of the stack, if the top of the stack is less than or equal the current value, then we want to pop it. That's, like we said, that's not going to be an answer. So now there are two possibilities. Either the stack is empty or we found a greater element, the next greater element. So if, like we said, if it's empty, we're going to make the index n, like we said, and otherwise the top of the stack is going to be the next greater element. And now we add the ith element and we're done. And we are also, this is the next greater element, but we also need the previous greater element to find the whole range, the whole subarray the maximal subarray. So I think the easiest way to do this is to copy paste. I try to make some reusable function for both, but I didn't quite make it to be to have a simple interface. So I think the best idea, so instead of next, this is going to be previous greater element. And there is a catch here, because when we go to the next one, it doesn't matter if we find one that is equal to the current one. We can also continue. We only want one that is strictly greater because of the tie-breaking condition. If it's the same, we're going to prefer the one that has the smallest index. But in this case, it's greater or equal when we go to the left. So let's make sure that we deal with that. But the code is pretty much the same. The only difference is that we go from left to right. And here, this is strict. So if we find, so maybe we could call this greater or equal element to be more explicit. And the other thing is, instead of n, if there is no previous greater or equal element, we want -1. And now we're ready. We've done all the pre-calculation that we need. So let's dive into the meat of the solution. So the NGE is going to be calc NGE of the score, and the PGEE is going to be the calc PGEE of the score. Then this is going to be a product, so the initial value is going to be 1, and like we said, we want to go over this from largest to smallest, and there's a trick to do that I usually use, is to sort a list of indices using as the comparison key when in this case is the nums of I, and we want from from greatest to smallest, and this is going to give us the order that maximizes the product. So now we want to find the NGE of I and the PGEE of I, and maybe for this I can draw something. So here we are considering the ith element in the array, and we have this NGE of I, let's say here, and we have this, well, sorry for the drawing, the PGEE of I right here, and this defines a subarray, the maximal subarray. If we include this element, this has a value x, which is the greatest at this point. We want to multiply by x as much as we can. But if we include this element, then this is going to dominate. This is going to be the one that is multiplied. So we cannot include this, and we cannot include this. Okay? And so all the subarrays contained in this maximal subarray are going to have x as the score. And how many are there? Well, as the leftmost element, we can have all the elements in here. We can have this one or this one or this one up to x inclusive. And for the rightmost, it's the same. We can have this one or this one or this one up to x. So that means that all the subarrays that are included in this maximal subarray are the product of all the possible left sides and all the possible right sides. So in terms of code, that is going to look like this. And that's why we use these special values, these sentinels, so that it works even, because here this position could be n, could be outside the array, it doesn't matter, or this could be -1, and this is going to work anyways. So we said that this is going to be a product, and since this is the next one, which is greater than the ith element, and this is the number of right sides of the subarray, and this is the number of left sides of the subarray. And this defines all the subarrays that are going to have x. So let's call this have, because this is the how many we can use, can or have, whatever, that we can add to the product. But remember that we are bounded by k. So what we can use effectively is let's call it count. Is going to be the minimum between what we have and limited by k. So now it's just about multiplying by nums I count times, and that is a power. That is just computing the power, which in Python we can do this way. We want nums I to count, but the mod, and of course this is only modding the power, but we are also multiplying by the power by res, so we need to also do this, and then we subtract the count from the bound, from the limit, and I think this should be it. Let's see if it works. Runtime error. Okay, so this is just a syntax problem. Okay, the expected answer is right for the examples. That's good. Is there some special case, some edge case that we can try easily? What happens if there are only ones? Does it matter? No, I guess not. Well, I mean, we can always try. I don't know if it's an important case. Okay, so here they give you the expected answer, but I think during the contest they don't. In any case, since we're only multiplying by 1, it's obviously going to be 1. So let's try our luck. Accepted. Cool. That's cool. So yes, so there are many takeaways in these problems, I think. Well, like I said, this is an overloaded medium, I would call it. It's an overloaded medium that becomes a hard because all these sub-problems add up. And it turns out to be a substantial amount of code. And you need to know some classic problems, but I don't think, I mean, the only hard part, in my opinion, once you know all the other sub-problems, is to figure out the core idea, the greedy decision, the greedy choice. And so remember to study the sieve, the factoring sieve, then and then the NGE, the next greater element, that's the monotonic stack. That's very useful for interviews, I think. And yeah, I think that's it. That's all I have for now. Maybe I can share my submissions, but I don't think after the contest. Maybe if I go to the problems, I can find them. Yeah, I think I think that I can find them here and I can share them if you're interested. Yeah, that's cool. Okay, so this is Q1. This is Q2. This is Q3. And this is Q4. All right. So yes, that's all I have for now. Thanks for watching. I'm gonna export the VOD to YouTube if you wanna check it out. So thanks a lot and see you in the next one. Bye bye.